before I forget, do you remember the sample variance, the one that Slutsky used to simplify the central limit theorem a bit? In some cases, we are not only interested in testing whether the expected mean and the sample mean of an experiment match, but we're also interested to see whether the sample variance is below an expected variance. Maybe not exactly equal to the expected variance, but at least below. For example, if you have a machine producing mechanical parts, or if you have a 3D printer, then you get an outcome that is, well, should have a certain shape, should have a certain size, and that size cannot be exactly determined or built the way it is supposed to be built. So what you want to specify is that the variance around this size is kept small. And if you want to test whether that machine operates according to spec, you are going to look at samples and you are going to try to see if the sample variance is indeed below the expected or the specified variance. Now, a nice little thing to know in this case is that the distribution of the normalized stochastic, I've called it Zn now, don't confuse it with that one in the central limit theorem, this is a completely different one. Zn is equal to n minus the sample variance divided by the expected variance. And if you take that stochastic, it converges as well to the chi-square distribution that we've seen before, but this time with a number of degrees of freedom, n minus 1, where n is simply the number of experiments that I did. So, if you want to test with a confidence level alpha whether the variance of your experiment is below a value sigma squared, then just compute this Zn and compare it to the chi-square quantile as you've learned to do before. That little trick will turn out very useful during the assignments.